Mean absolute error. The next regression loss function that we are going to learn is mean absolute error. We already learned about mean squared error, which is the first regression loss function that we looked into. The next one is mean absolute error. Let us first see what exactly is mean absolute error. Well, let us see how to write the equation first. From there, we'll start. As the name suggests, mean absolute error. Let us start with the term error, then we'll see what is absolute error, and then we'll see what is mean absolute error. Okay? Error is the difference between actual value, which is yi, and the predicted value, which is yi cap. What is actual value here? When you have a model, let us say this is your model. Through this model, if you pass an input xi is your input. Let us say you have a pair xi, yi, where xi is the input and yi is the expected output. What will your model do? Your model will take xi as the input and it will produce an output called yi cap. So we'll call this as predicted value. This is the value that is predicted by the model. Ideally, you should have yi, but your model predicted it as yi cap. So the difference between the ideal value, which is yi, and the value that is predicted by the model, that is yi cap, this is called as error. The next thing is, what is absolute error? Absolute error means you have to take the modulus, mode of yi minus yi cap. This is called as absolute error. The next step is mean absolute error. If you want to find mean of anything, let us say there are n samples and you want to find the mean value of these n samples, what will you do? You will do 1 by n, sigma I is equal to 1 to n, si, where si is the ith sample. The same way, here you are taking mean of absolute error, which is yi minus yi cap. So how will you find the mean absolute error? You will do 1 by n, sigma I is equal to 1 to n. You will take this absolute error, mode of yi minus yi cap. This is your mean absolute error. So at this point, you can understand that this mean absolute error measures the average absolute difference between predictions and the actual values. So this is the significance. So intuition is like this. On average, how much are your predictions off from your actual values? This is the intuition behind mean absolute error. Let us see what are the properties, what specialities are there with this mean absolute error. See, simply understanding the formula is not enough. You need to understand what exactly is the speciality of this particular loss function, what are the advantages of using this loss function, and this will guide you in order to use it in the right instances. You will know when to use it only if you clearly understand what is the requirement of this loss function, what exactly are the advantages. So the properties, first property is that errors always grow linearly. They never grow exponentially also. Here it always grows linearly. In case of mean squared error, we had seen that as the error increases, growth also increases by a very large margin. Why is that? Because you were squaring errors. Because you were squaring, if your actual error, that is yi minus yi cap, if that is 1, when squared, it will stay 1 itself. But if it is 2, when squared, it will become 4. If it is 3, when squared, it will become 9. Which means your errors will grow in an exponential manner or in a squared manner. But in case of mean absolute error, what happens? Whatever is your actual error, the absolute value of that will be taken. So in case of 1, it will stay as 1 itself. In case of 2, it will stay as 2 itself. In case of 3, it stays as 3 itself. This is the first speciality. Now you can ask, why did you teach us the other one and say that that has an advantage that larger errors are penalized by a large extent? That is because All these depends on the use case. In some particular problem, while building one particular model, you may want this model to behave such that the larger errors should be penalized largely. That is, you want all the predictions to be somewhere close to the actual one. There may be another case, another model in which you actually want to penalize exactly as per the absolute error. So all this depends on use cases. You need to understand what this loss function is doing, and then when you get an actual problem, while you're solving the problem, you have to analyze which is the actual error function to be used. Okay. The second advantage, first one is that error grows linearly. Second advantage is that it is robust to outliers. So this point again, in the last case when we were learning about MSE, mean squared error, we said that whenever you see any of the outliers, they will always dominate the loss. We said that outliers will affect the loss by a large margin. That is because of squaring. Here we are saying it is robust to outliers, and we are saying this as a positive point here. Why is it a positive? It is positive only in those cases where you want this quality that you have to behave robust to outliers. In case it is not, then you should go for MSC. So here I am making sure that you understand where to use MSC and where to use MAE. So you want to understand the logic behind these. Then once you get a problem statement, you can choose. Okay. Then the third speciality is that when we were learning about MSC, we told that it should be used whenever you have Gaussian noise. That is, whenever you have Gaussian noise, and when you minimize MSC, then we said that you should be using MSC as the loss function. The same way, if you are having a Laplace noise, in that case, you should be using MAE as the loss function instead of MSC, which you were assuming Gaussian noise. If you are assuming Laplace noise, then you should use MAE as the loss function. The next question is, what is Laplace noise? What is Gaussian noise? So for now, you just understand that in case of Gaussian, you will have a bell curve like this. And in case of Laplace, you will have a curve that is pointed at the mean and with a heavier tail. So basically you need to understand this. In case of Gaussian, tail will be very thinner. But in case of Laplace, tail will be slightly thicker. That is, compared to Gaussian, you will have a thicker tail or a heavier tail in case of Laplace. Moreover, you will have a pointed head. The top of your graph, that will be pointed. The peak of your graph will be pointed. This is Laplace. In case of Gaussian, it will be round shaped, right? So the next thing is, what is the difference between these two things? The main difference is, whenever you are thinking of Gaussian, you are thinking of mean. But when you are thinking about Laplace, you are actually thinking about median. How do you understand this? Another way of understanding is, let us say you are minimizing MAE. You have mean absolute error and you are minimizing MAE. So the prediction that you have, that will be median of the target distribution. But in case of MSE, mean squared error, when you are minimizing mean squared error, the prediction that you have will be mean of the target distribution. This is the difference. So basically the question is whether you want median or you want mean, right? So accordingly, you have to choose the error function or the loss function. The next point is there any special disadvantage for this MAE? Till this point, whatever we discussed, all these things are, I'll point this also here, median and mean. Okay, this is the fourth point here, that MAE always provides you median of the target distribution. At this point, next thing you have to ask is, all these points, they are not positives or negatives. You can say in one way MSC is better, another way MAE is better. Is there something on which there is a negative on MAE, the mean absolute error? The negative point is MAE, it is not differentiable at y is equal to y cap. In case of MSE, mean squared error, we told that it is differentiable everywhere, but in case of mean absolute error, it is not differentiable at y is equal to y cap. We'll take the gradient and understand this clearly, why it is not differentiable. Before that, okay, first we'll take gradient so that it will be clear for you, then we'll move forward, okay? Let us take the gradient and understand. If we remove this, okay, so this is your mean absolute error. I'm going to take gradient. So for now, let us take just one point, okay? So loss of, I'll say y cap, for one particular point, loss will be y minus y cap. Let us say this is my loss. If this is my loss, this is my residual value. I'll call my residual value as E. E is equal to y minus y cap. This is my residual value. And what is my loss? Loss can be written as mod E, because loss is mod of y minus y cap. So I can write it as mod of E. The next thing is I'm going to differentiate this residual. I have the residual here. So with respect to residual, if I differentiate the loss, what happens? That is d by dE of the loss. So of mod E. If I do this, I will get, this is my E. So if I differentiate, what will I get? I am differentiating with respect to E only. I am not differentiating with respect to y or y cap here. There is a reason I am doing this, okay? In the next step, you will understand why I am differentiating with respect to E. For now, just go with the flow. So if I simply do d by dE of mod E, what will I get? It will be plus 1 if E is greater than 0, and it will be minus 1 if E is less than 0. This is very simple, you already know. One more thing, I'll clarify here. E greater than 0. What does that mean? E is y minus y cap. So if E is y minus y cap, then E greater than 0 automatically means y is greater than y cap. This is the case here. Similarly, if this value E is lesser than 0, that means y cap is greater than y, right? These are the cases. For now, just see this. I have this. I'm going to use this particular one. d by dE of mod E. Okay. And one more thing, at E equal to 0. What happens at E equal to 0? Modular function at 0. It is undefined. It is not differentiable. Why is it not differentiable? It is because if you take the left derivative, it is not differentiable. Okay. Because if you take the left derivative of mod E with respect to E, you will get minus 1. If you take the right derivative on the right side, you will get plus 1. So because it is minus 1 on left side, plus 1 on right side, that means it is not differentiable. This is why at the point E equal to 0, it is not differentiable. Still, you can take the subgradient. So generally what you can do is, because subgradient is possible, you will say from minus 1 to 1, you will take any value. Generally, you take the value 0. This is how you generally handle this scenario. Okay. So the next thing, I'm going to take the gradient of this whole thing. This is just the first step that I did. Next step, what I'm going to do is, I want to find the actual gradient. That is d by dy cap. Y cap is the predicted value. With respect to the predicted value, I want to find gradient of loss. How am I going to do this? Loss is this, which I know is mod E. I'm going to use the chain rule here. According to the chain rule, if I want to find gradient of mod E, that is d by dy cap of mod E. If I want to find this, what can I do? I can do d by dE of mod E into dE by dy cap. This is chain rule. I used chain rule here. Okay. The reason I use chain rule is, this part is very simple. What is dE by dy cap? My E is y minus y cap, which means dE by dy cap, this value is minus 1. Why is it minus 1? Here y cap is having negative value, which means if I differentiate this with respect to y cap, I will get minus 1. So my dE by dy cap, this will be minus 1, which means dL by dy cap will be negative of dE by dE. d by dE of mod E. And this value I already calculated, I have it here, which means if I just reverse the signs of whatever I got here, I will get d by dy cap of dl. So how can I do that? So here I can write, I can just take negative of these things. That is, instead of plus 1, I can now say it will be minus 1 if E greater than 0. So instead of E greater than 0, I can write Y greater than Y cap. And the next one here, instead of minus 1, I am going to write plus 1 if Y cap is greater than Y. And what about the case when Y cap is equal to Y? In this case, we told it is not differentiable, but you take the subgradients, then you can say it is element of minus 1 to 1. Generally, you will take 0 here, but you can take any value, okay? So now, what about the gradient of full MAE? Here I took the gradient of loss. So if you take the complete MAE, that is 1 by n sigma I equal to 1, yi minus yi cap, instead of just this one loss, if you take that complete MAE, then what will you get now? If you do that, you will get something like del by del with respect to one particular prediction, you are going to take the derivative. If you take the derivative of MAE, what will you get? You will have the 1 by n. If you see here, you will understand that the 1 by n part will remain there. But from this complete addition that is over here, only one particular value will be corresponding to yi. So when I differentiate, it will be 1 by n into whatever value we found here, that is minus 1. So I'll just direct it to here, 1 by n into, or I'll write minus 1 if y is greater than y cap. I'm just copying from here, okay? Plus 1 if y cap is greater than y, and element of minus 1 to 1 if y cap is equal to y. So this is how you can find the gradient of MAE. So I just wanted you to clearly understand gradient of MAE so that I can put forward the next point. What is my next point? My next point is that gradient is piecewise constant. What is piecewise constant? Here the gradient is minus 1 or plus 1. It does not depend on the error. This is a very important point. Your error is y minus y cap. Your value of gradient, it is not at all dependent on the error. It is plus 1 or minus 1, which means it is piecewise constant and does not depend on the size of error. So when I said does not depend on the error, that means does not depend on the size of error. Okay, the gradient will be minus 1 or plus 1. So what does that mean? When I say gradient is piecewise constant, it does not depend on the value of error. What does that mean? That means when you are optimizing this, when you are using it in a gradient descent or you are optimizing, MAE can be slower. The reason is it cannot push harder if the errors are large. Even if the errors are large, it will push by the same value. That is why convergence can be slower in case of MAE. So I didn't want to simply make a statement that convergence is slower. I wanted to show you by differentiating, and then I wanted to show you that it is piecewise constant. Because it is piecewise constant, optimization can be slower, right? So I want you to understand this logically. One last point before we conclude this lecture, I want to make one more point, that is, where should you use MAE? This is what you want to understand. Where are you going to use? First case is when outliers are expected in data. When you have outliers which are an expected scenario, then you don't want to penalize these outliers largely. What are outliers? Those are the points which are far from your median or far from your mean. So these outlier points, if you don't want to penalize largely, you will use MAE. This is the first point. Second point is when interpretability matters. What is interpretability? Let us say you want to explain this to someone, a manager or someone who is non-technical, or maybe a client or someone. If you want to explain this to a non-technical person, it's much easier with MAE because you have the results in terms of the actual values. In the same scale itself, you have the errors. And it's easier to explain instead of going and explaining you want to square it as this logic and all. MA is much simpler to explain. Then generally, where do you see this MAE, mean absolute error? So generally, you see this in forecasting problems or competition metrics, these sort of things. You generally see mean absolute error being used. And one more thing we already told about this is that if the noise is Laplacian, if the noise is Gaussian, you will go for mean squared error. If the noise is Laplacian, then you will go for mean absolute error. So this is it about mean absolute error.